So let's spend a few moments talking about relative standing. So by relative standing, um, it's an idea that says, maybe relative to your classmates, where do you stand compared to others? And so we're familiar, most likely, with a ranking system, right? If you have maybe 200 people in your class, your graduating class. And let's say that your score on a particular test or your overall GPA, if you rank them in order, maybe yours is right in the middle. And if that's the case, then your score is kind of better than 50% of, say, the rest of your class. Your ranking would be a 50 percentile, right? It's the 50th percentile is what your ranking would be. So it's a way of just kind of seeing where you are relative to the other, one relative to another. And so when thinking about scores and putting them in order and then just counting how many are below your score, that one's a little bit more intuitive than another method that's based on the z-score. So let's take a look at the z-score. So for example, if I want to compare ACT versus SAT, these standardized scores. And now, what's interesting about these two tests is that they are on different scales. So we can't just simply do what most of us see well over 90% of the time. We just simply take a percentage. That's intuitive. But when it comes to a scale that is not 0 to 100, but rather say 1 to 36 or 400 to 1600 for these two different tests, how do you compare one versus the other? So these are different scales. For example, is a score on the ACT of 27 any better? So a score of 27 on the ACT, and let's compare that to a score of 13, 18. Which one of those is better between the two, right? So, in fact, just looking at the numbers is not enough, and you can't divide, for example, 1300 by 1600. You can't do that simply because that is not the entire range. You can't just divide 18 by 1600. Had this been 0 to 1600, that would have been a possibility. So we need a way of comparing scores. So now, one thing that's also true about these two standardized tests is that these scores, both, if you were to place the entire population of student scores into a histogram, you would see that those scores, right, if I take a score and give it a range, and let's say that the mean score for the ACT, let's say that the mean score is 20.9. So if you were to kind of split this up into a range of scores, remember it goes from 1 to 36. If you were to split this up and just start kind of counting up the frequency within a range, within a bin, how many people got maybe between 17 and 18? How many folks got a score between 18 and 19? This would be a pretty dense histogram, right? It would look more like an infinite number of dots. And so we're going to use the normal distribution, this normal curve, to represent kind of how these scores are distributed. Now, so ACT scores do follow a normal distribution, and I'm going to use this shorthand technique for saying number 1 is normal. I'll use an N. And then not only is it normal, there's a mean and the standard deviation. So the mean is 20.9. and the standard deviation is 4.8. For SAT scores, it's also a normal distribution, and it has a mean, right? The mean score for this particular test in this particular year had a mean score of 1026 and a standard deviation of 209, so 209. So what's interesting about both of those tests, right? Number one, they both follow a normal distribution. So they really have a similar pattern where they have, they can be described, if I were to graph it, by this rather complicated function that we see here. Now, really this is simply, a function of x. If I give me some x values, I could plot the corresponding y values. Now, what makes it a little bit more complicated is that we have a couple of other constants here. You'll see an a and you'll see a b. So those values help us fix this particular curve. Other than that, it's just a function of x. But those values of a and b fix the curve to correspond to that data set. So the way this works is that the value of b in this case is the mean, and the value of a corresponds to the standard deviation. So as long as you know the mean and the standard deviation of your data set, the only thing left that's unknown is the score itself. So you can plot that curve. So now what that curve would look like is something like what we see here. So this is the standard normal distribution, and the value of b represents the mean. So the curve, though, depending on which test you're looking at, tests are going to have different means. And this could kind of shift depending on what that test is. And so that kind of curve is going to change based on the data, but in general, it's all described by this one particular function. So now let's go back to this. So how do we compare these two? So if you look at this, let's say that Tina, we're going to do a comparison. Let's zoom in on this a little bit. Tina has a score on the ACT. Let's say that Tina has an Tina took the SAT, so I'll make it the same color. So Tina has a score on the ACT, or the SAT rather, SAT score, and her score was 1318. Now, and then let's consider Jane, who took the ACT. And on this particular test, Jane ended up with a 27. So the question for us then is, which score is better? How can you compare one versus the other? Well, one way to do this, one way to think about this is to remember that they are both on, both curves fall within a normal distribution. One normal distribution had a score of, had a mean of 1026. Let's show that there. And the other normal distribution had a mean of 20.9. And so the 1318 that Tina got would have placed her in that histogram, kind of in this spot over here. And then the 27 that Jane got would have placed her over here. So what we're going to do is say that, well, that 1318 corresponds to a certain point where everyone here on the left had a score that was less than. And that's for the 1318. For the 27, everyone over here on the left had a score that was less than. So what I could do is then basically determine, number one, what percentage of the area is to the left of Tina's score, and then what percentage to the left is to the left of Jane's score. And the person whose score is greater than the largest percentage of individuals then certainly achieved a better score. So that's one way to think about it, and we'll see that in a second. The other way to think about this is how far above the mean did Tina score? So now we can't just simply, there are some challenges in fact with just simply saying, well, how far above the mean? 1318 minus 1026, and then 27 minus 20.9. So both of those are numbers that will tell you how far above the mean a particular individual scored. But these are two different scales, so that has a few problems. So which is better is going to be determined. So which is better is going to be determined partially by, so determined by measuring the distance above or below the mean. So distance above or below, I'll just say distance from the mean. Now, there is this one issue of scaling that we have to think about. So since this is a fixed curve, this normal distribution curve, it follows a pattern where there is a particular standard deviation that captures 68% of the individuals. That's one standard deviation. So we know a few things about these curves. And even though this one is on the one with Jane is on a different scale, it also has a standard deviation. All right? So what we could do is say, well, how many standard deviations away is that value? Versus how many standard deviations away is Tina's score? That's one way to start thinking about this. So we need to make sure we scale it. So how could we do that? Well, let's think about this. Let's kind of generalize this idea of scaling. So a bit of a diversion. Let's think about scaling for a minute. If I give you the number 300 and I ask you how many centuries are in 300, how many centuries? I'm pretty sure you would say, well, 300, clearly that's going to be 3 centuries, because each century, a century is 100. So what you've done really is you said, well, it's 300 years, and you want to know how many centuries. Well, you also, so since that's 300 years, we also know that it's 100 years per century. And so the units just kind of work out really nicely so that we end up with 3 centuries. So even if you're not comfortable with the math of the units, there's an intuitive sense about there being 100 years per century. Another example for scaling might be given the number 36, how many dozens? If you have 36 eggs, for example, how many dozens? Well, you automatically, hopefully, might start to think about this in groups of 12. And so at some, maybe an intuitive level, you would take your 36 eggs and you would divide them by 12, since there are 12 eggs per dozen. And what you're left with is, in fact, 3 dozen eggs. So now, what I want to do is think about how many standard deviations. I want this to be in units of standard deviations for these scores that I'm looking at. I want to know the distance from the mean, but in terms of standard deviations. So Tina's score, distance from the mean, let's go ahead and calculate those values. So let's come over here. So for the first distance from the mean, we have Tina's distance from the mean, 1318 minus 1026. She's 292 units. 292 is the difference. And for Jane, the difference is 6.1. So those are the numbers. Tina's 292, Jane is 6.1. So therefore, for Tina, her score, which was 292, if I want to convert this into units of standard deviations, then I need to divide by the number of standard deviations for that particular data set. And so her score is 1.39. Standard deviations. And for Jane, her score, which was the 6.1, and divided by the standard deviations for that particular data set. And so we said that was, go back up, 4.8. So her score was 1.27 standard deviations. And so these are distances from the mean. These are distances from the mean. So in this generic kind of curve here, where we have a mean, and we have, for all of these normal distributions, there is some distance here above the mean, and some distance here beneath the mean. We do know that 68% is captured within one standard deviation, which means that there's 32 left. So there's 16 on this side and 16 on that side. So you get the 32 plus the 68 to give you a total of 100%. So that means that someone who scores one standard deviation above the mean has done better than 68 plus 16, which is going to be 84%. So in terms of standard deviations, anyone who has a score, just one standard deviation above the mean, has already achieved a score that's better than 68 plus 16, or 84%. But someone who's achieved a score that's 2 standard deviations above the mean, right? Multiply the number of standard deviations by 2 and add that to the mean. And let's look at the other side, number of standard deviations, and then minus the mean. At that point, that score is even higher than what we just saw, right? With the simple single mean. So someone who has scored 2 standard deviations above the mean, then don't forget 2 standard deviations captured 95%. So what we have left is 5%, which means 2.5 has to come over on that side, 2.5, and that captures 100% of all the possible scores. But anyone who has scored 2 standard deviations above the mean has done better than what's to the left of that. It looks like to the left is 97.5. So this person's score here is better than 97.5. So the more further right you go, the better your score is, because that also represents the how much better you did than some percentage of individuals on that particular test. So we want to count this in terms of units of standard deviations. So looking at these two, I would, given a choice, would you rather be 1 standard deviation above the mean? Or would you rather be 2 standard deviations above the mean? So 2 standard deviations means you've achieved a score that's higher, or certainly higher. Now, or you could have some number of standard deviations, right? We've put this into units, that difference from the mean in units of standard deviation. You could have something that's not a 1 or a 2, but maybe a 1.39 standard deviations. So Tina's score is 1.39 standard deviations above the mean. So this is further away from average. It's higher than average. So this would be a better score. Now, in general, right, we can take that what we've just done and generalize this. And we can say that the distance from the mean is going to be whatever the score is, and what we're going to subtract from that person's score, well, it's going to be the mean of the data set. And then what we're going to do is normalize it in terms of give it units of standard deviation for that data set. Just like we gave it units in terms of dozens or units in terms of centuries, we're going to give it units of standard deviations for that data set. So that's how we can get a difference. As this score is just how far away from the mean one is in the correct units. We're going to give it a name. We're going to call that difference a z-score. So a z-score is ultimately the number of standard deviations away from the mean, and this could be a positive or a negative value. So if your score is less than the mean, you could have a negative z-value. If it's above the mean, you could have a positive z-value. So, for example, let's say that, do a quick calculation, let's say that we have Fred, and his score is, let's say that Fred's score is 35. And this is on the ACT. What we also know about the ACT was that it followed a normal distribution, had a mean of 20.9, we had a standard deviation, right? They always follow in order, the mean and the standard deviation. We just kind of do this shorthand notation, had a standard deviation of 4.8. So Fred's score of 30, let's turn that into a z-score. His z-score is going to be 30, and then let's compare that to, let's look at how far away he is from the mean, and then let's scale this in terms of standard deviations. So Fred's z-score is 2.94. Now, is that a good score? Well, intuitively, what we do also, hopefully if we understand the empirical rule, right? The empirical rule said if you're 1 standard deviation above the mean, that captured 68%. But if you're 2 standard deviations above or below the mean, that represented 95% of all individuals. But if your score is 3 standard deviations above the mean, or if we're looking at 3 standard deviations, let's see if I can. So the empirical rule, what we learned is a score plus or minus 3 within that interval that captured 99.7% of all data points, of all scores, are going to be within plus or minus 3 standard deviations. So if you're 3 standard deviations above the mean, which is what Fred's z-score is, certainly there's 99.7% that he's done better than, at least 99.7%. But not only that, remember there's an additional 0.3% on either side. So 0.3, half of 0.3 is 0.15 and 0.15. So 99.7 plus 0.15, 99.7 plus 0.15 is a 0.85, 99.85, 99.9. So if you're 3 standard deviations, your score is better than nearly 99.9% of all scores. So z-scores tell you quite a bit. A z-score of 1 is pretty good. A z-score of 2 is even better. A z-score of 3 is highly unusual. Z-score of 4 is just off the charts. You'd be better than 99.999999% of all scores. So the z-score, think about it in terms of standard deviations, right? That's a good working idea of a good working kind of image to take with you when considering z-scores. And then finally, to take maybe one more simple example, let's look at Bob's score, and his score might have been, say, 19.9, and this is for the ACT. So what is Bob's z-score? Bob's z-score, just take his 19.9, we're going to follow the template where we do a subtraction from the mean, right? So the score will always be the value on the left side. And there's a 20.9 and a 4.8. So 19.9 minus the 20.9 ends up being a negative 1 all over 4.8. And just to make this, well, and we'll work with this. It's a negative z-score. And that z-score value is going to be 1 divided by 4.8. So 0.208. So if I round off, it becomes an approximation. So I'll say approximately negative 0.20833333. So since Bob's score is beneath the mean, it's a negative z-score. So it could be a negative, so he's just a fraction beneath the mean, but had he been, say, negative 1, then he would be 1 standard deviation below the mean. So negative 0.28 may not necessarily be the most informative value, but had there been a score of, let's say, z equals -1, it adds intuition, right? Because at z equals -1, given that the mean is 20.9 and 1 standard deviation captures 68% with 32 left, so 16 and 16, at someone who has a z-score of -1, to the left of that value is 16%. So someone who scores a value where z is -1, they ultimately get a score with a z-value of -1. They've done better than 16%, but also 84% has done better. So a z-value of -1 is a bit low. So my question is, if you have a z-value of -1, what is the corresponding score that goes with that z-value? And so we can work the math on that. We don't know what that score is, but we can work backwards and figure out what that what the score was to get a -1. So we know it should be less than 20. It has to be less than 20.9. So let's do the math. We're going to multiply by 4.8 on both sides. And so let's do that. Let's see if we can bring that back in. So 4.8 on both sides. And we end up with -4.8 on the left, and we end up with just simply x minus 20.9 on the right. And let's go ahead and add 20.9 to both sides. So you get -4.8 plus 20.9 equals x. So the score that would give you a z-value of -1 would be x equals 20.9 plus or minus 4.8. So 20.9 minus 4.8, or 16.1. So 16.1 corresponds to a z-value of -1. Oops, let's make sure it's negative. So anytime you have a score that's below the mean, it's going to also give you a negative z-value. Above the mean would be a positive z-value. So in general, if you want to go the other direction, let's write that here, where you are given a z-value and you wish to find what that score is that corresponds to that z-value, there's another formula that's going to give it to you, right? Remember, we were given a z-value and we want to find out what that x-value is that's going to give you that score, and these are always going to be a given, mu and sigma, and x is unknown, just like we did here. So let's follow the same pattern. We're going to multiply both sides by the denominator of that quotient. So we have z times sigma equals x minus mu. Again, and if we want to find that score, let's do the math and add mu to both sides, and I'll just kind of put this on the left. So x equals mu, whatever that mean is, plus z times sigma. So this would, given a z-value, this is how you could convert that z-value to a score. And since 95% of all kind of events on a normal distribution happen within 2 standard deviations, what we're going to do is say z-values between -2 and +2, those are considered usual or expected. If you get a z-value that's greater than 2 or less than a -2, then that is highly unusual. So how far above the mean does a score need to be for us to say that the z-value is unusual? Well, what's usual is anything within the interval -2 to 2. Those will generally not be surprising values. But if you go and if someone has a score that's beyond that, z-value of 3 is better than over 99% of all scores. Z-values of 2, 95% of the time you expect the score to be within -2 and 2, or at least 95% of the scores are there between -2 and +2.